Hello, I am Veniero Lenzi, from the Center of Physics of the University of Minho in Portugal. In this poster, I will show you the research that we are performing within the MacTool21 project. In particular, I will talk you about how we are developing atomistic models to simulate titanium and silicon nitride and silver nanocomposite coatings. In aerospace industry, the use of novel lightweight and high-performance materials is one of the most important ways to reduce its carbon footprint. However, what makes these materials appealing also makes them hard to work in machine, with the results that standard machining and cutting tools are easily broken. To overcome this problem, a possibility is represented by the use of self-lubricating coatings, since they have been shown to enhance the lifetimes of machining and cutting tools, with clear advantages in terms of economic and environmental sustainability of the materials processing. Titanium and silicon nitride nanocomposite coatings, in which dispersed silver nanoparticles are the lubricating agents, are very promising in this sense. Those coatings are formed by many grains, which generates a complex nanostructure, where many grain boundaries and void intergranular spaces are present. The silver transport rate is fundamental in defining the final coating's performance, because silver must diffuse in a controlled way, not too fast to avoid its premature loss, nor too slow or the lubricating effect won't be present. However, a full understanding of the diffusion process is out of reach, due to the high complexity of the coating itself and the dependence of silver transport from the nanostructure. Hence, our objective is to use atomistic modeling and simulation techniques to gain insight on how silver diffuses across the self-lubricating nanocomposite coatings. In this regard, we already developed a hybrid classical force field for titanium nitride and silver systems, which was parameterized to reproduce the adhesion energies of silver on titanium nitride surfaces and the defect formation energies of titanium nitride and silver systems. We used it to run molecular dynamics simulations in order to evaluate the different possible diffusion mechanisms of silver within titanium nitride. And we found that, while the diffusion in bulk is prohibited and the diffusion along grain boundaries is very slow, the diffusion along surfaces, which happens in correspondence of the intergrain spaces, is the dominant process behind silver transport. Unfortunately, this atomistic model cannot be expanded in order to include silicon nitride, because the interaction between titanium and silicon and between silicon and silver is hard to model. In this research, we plan to use machine learning techniques to solve this problem and to obtain an atomistic model capable of dealing with titanium, silicon nitride and silver system at the same moment. In particular, we will rely on a model trained using on-the-fly approaches based upon simulations performed for a diverse set of representative input structure. Because in machining and cutting processes, high temperatures are expected and it is very important to include temperature effects in the model, the training will be performed on a wide range of temperatures. The final trained model, which is based on Gaussian processes, will produce a force field that could be readily used for classical molecular dynamics simulations, thus enabling large-scale simulations of titanium, silicon nitride and silver systems. And beside this, it will also be capable to outperform the existing parameterizations in terms of accuracy, because the trained model will be based upon first principles calculations. The machine learning model will be used not only to fully understand the silver diffusion behavior, but also to gain insight into the mechanical and stability properties of the nanocomposite coatings, providing by this a powerful tool to optimize the coating performance. Thank you for your attention, and if you have questions or are simply interested in the topic, feel free to contact me.